All right. Yeah, thank you very much for this introduction. So I'm Anton Lorenzen, and I'm presenting this work, which is done in collaboration with Daan Leijen from Microsoft Research, Wouter Swierstra from the University of Utrecht, and Lindley from the University of Edinburgh. And so the title of our work is First-Order Laziness. And to start talking about what first-order laziness is, I want to first contrast it against what I call higher-order laziness. So this is how you would normally implement laziness in a strict language like OCaml, for example, or in this case, Coca. You have one type, thunk A, which is usually left abstract, and it has two functions, delay and force. So delay takes a closure that goes from unit to A, and force takes a thunk and gives you the result of the closure. And so the important thing about this interface is that the delay function only stores the closure and does not run it in particularly. But then force will run the closure once the first time it is invoked and memoize the result afterwards. And so these are the two things that really make up this lazy interface, is that the function is evaluated only once you actually call force, so you can kind of delay a computation, and that the result is memoized for all future calls for force. And we'll come back to these two principles later. Now, let's look at one concrete example for how you would use this interface, and I'll consider streams. So a lazy stream is some stream type A, and you have an scons constructor for like one element on the top of the stream, and you can also append two streams lazily. And so what you can do with this interface is that you can, for example, create a thunk that will run an sappend between two streams, one stream that has a 1 in front and then has some unknown S1, and I append this on top of S2. And what most programming languages do if you run something like this on the console is that they just tell you, oh, this is a thunk, but I maybe don't really know what it is. And now, of course, you can force this thunk, and then you can see, okay, I'll do like one step of the append function, and I'll see it's an scons 1 in front, but I still don't really know what's in the rest. And so we'd maybe like to look into it. We'd maybe like to say, oh, actually, at this point, like if I've done like one step of the append, I'll still have to append S1 to S2. But usually this is not really possible. And really the reason it's not possible is that this delay thing is a closure, and most programming languages can't really print closures. So So the question I want to ask in this talk is, should laziness be higher order? Because if you think of this delay function, it really, like this idea that you need to supply a closure is really built into this interface. You can't, for example, like supply a constructor or something. And so the fact that delay must take a closure introduces a lot of weird effects. In particular, it makes it a lot harder to reason about the laziness you have, both for the programmers and also the compiler. So in particular, the closure you have in the thunk can usually not be printed on the console. You don't also really know whether a thunk has been evaluated yet or not, which makes it a bit harder for you to reason about the performance of your program. But even if you can reason about the performance, it may not actually be that good, because this delay function will actually incur two separate new allocations, one to create the outer thunk, and then a second one to create the closure that you put into it. And so, I mean, I work a lot on something called Perseus reference counting, and so in Perseus reference counting, it's actually not that bad to have more allocations if you can reuse them. But in particular, Perseus reference counting cannot reuse closures, which means that also, in particular in a language like Coca, this interface is actually not very good. So what I want to show in this talk is that we can solve all of these problems if we take a new approach to laziness. And the idea is, what I want to do is I want to defunctionalize the laziness from a higher order to a first order representation. Let's look at how that works. So let's actually implement the stream data type. So we have a stream of A's, which consists of an scons constructor that has a head and a tail, and a nil. And so you can see that at this point, it's very much isomorphic to a list, and we'll now add some laziness to it. And the way we do this is by a new language feature that we call lazy constructors. So we'll create a new constructor, sappend, for a lazy append that we want to do between two streams. And so we write this lazy keyword in front to show that it is a lazy constructor. And the important thing you need to do with a lazy constructor is that you need to give a definition for it, which I've done here. And you can see that this definition kind of follows the normal append function you would write. I look at whether the first stream is a cons or a null, and then either if it's empty, I'll return S2, and if there's some more, I'll return the first element of S1, and then keep appending. So how do these lazy constructors work? If you create a lazy constructor, it works very much like a normal constructor. So in particular, if you create a new lazy constructor like sappend, it is just a normal value, and nothing much happens. The important thing is what happens if you actually match on them. So in the normal traditional interface, a lazy thunk is evaluated by force. But lazy constructors are evaluated by matching on them. So to look at an example, we can consider the length function. So the length function of a stream is very much like you would imagine the length function also for a list to be. And let's evaluate the length of a lazy constructor that consists of appending the stream 1 in front of S1 to S2. So the first thing we do is, of course, inline the definition of length, and we see that the first thing we do is actually match on the stream that we've provided. And you can see that there's something that doesn't quite work because we do not actually match on the lazy constructor. We only match on cons and nil. So how does the compiler do this? The idea is that the compiler now looks up the definition we have in the stream, and in particular looks up the definition of the lazy constructor to rewrite the lazy constructor to this definition. So what we'll do is we'll turn the sappend that we were matching on into the definition where we first destruct the first argument of sappend and then either return scons of sappend or just S2. And now, of course, we can evaluate the inner match, and we just get a match of scons1 on sappend S1 and S2, which just by the definition of length evaluates to 1 plus the length of the rest of the appended stream. Right. So we can see that the first part of laziness actually happens here. We evaluate lazy constructors on every match. The second principle of what laziness has to do is about memoization. The result of a lazy constructor should be memoized on all future matches. So in particular, let's say I have my lazy constructor here and I bind it to the name S. Then if I perform a match on it, it has to be evaluated to a cons. And after that, it stays evaluated like this. So again, the memoization is happening here, which in particular means that, for example, we can actually model the original delay interface using lazy constructors. So what we'll do is we'll have the stream data type, where we now add one extra constructor that I call sDelay, that takes a closure f from unit to stream A, and the definition is just to invoke this function. So the way I would implement delay now is by just wrapping the function f into an sDelay, and the way you would implement forcing is by matching on the stream to actually evaluate it to one of the regular constructors. Now, the reason why this is such a nice thing is because it means we can apply lazy constructors in our program exactly when we want them, and we're not really forced to make any lazy computation into a lazy constructor. This is in particular important because defunctionalization can be a whole program transformation, but this basically allows us to make lazy computations into lazy constructors if we want to, and we get a benefit from them, but we don't have to do it if we feel like it would be too involved. But of course, sDelay also provides no benefit over the interface we've had before. So I want to talk a bit more about what really the benefits are of having a lazy constructor in this special interface versus having like this general delay interface. And one of the benefits, I think, is that you can kind of peek under the hood a bit to understand what your lazy program is really doing. And in particular is we have a new language feature that we call lazy match that allows us to inspect for a data type which lazy constructor it is. And you can use this, for example, to implement a show function. So if we want to show a stream on the command line, we might want to see where there's still an append happening. And the idea is that we can use lazy match to figure out, is this an sappend constructor or not? And if so, we just print the sappend directly on the command line, which is kind of gives you the nice printing behavior that I've shown you before. And I think this is actually really good for debugging in practice if you program with these data structures. But I also want to kind of caution a little bit. So one of the really big benefits of laziness is something called referential transparency. And lazy match breaks referential transparency. So the idea is that this memoization that happens in laziness should be an unobservable side effect, in the sense that the semantics of your program does not allow you to see whether a thunk has been forced or not. And of course, if you show a stream with some sappends in there, and then you take the length of the stream, you will fully evaluate it, and suddenly, if you show it again, it will look very different. So the lazy match does break it. But however, the regular match actually does preserve the referential transparency, because the regular match only lets you look at actually the normal strict constructors and does not allow you to observe the lazy constructors. So, which means that actually if you're very careful in your use of lazy match and maybe only use it for debugging, you actually still get all of the normal reasoning benefits of laziness, even with this approach. Now, I want to talk a bit more about lazy match, in particular because it is very useful also to implement lazy constructors in a good way. And so how would we actually compile something like the stream data type in the compiler? And the idea is that we basically generate an evaluation function that kind of takes a stream and will give you an evaluated version of it back. So the thing we do on the stream in this evaluation function is we lazy match on it, and if it's a nil or a cons, we just return the nil or cons. But in particular, if it is an sappend, we'll have to use the definition of the lazy constructor to evaluate it further. And there's a few things here. So in particular, sappend can return this S2 in the end, which again might be a lazy constructor. So what we're doing there is we're actually writing an indirection node, and we keep evaluating S2. And of course, to do the pattern match on S1 in the first place, we have to recursively call eval here to make sure we really only pattern match on an evaluated thing. And so once we have this representation, we can actually do a whole lot of optimizations on it. And in particular, one optimization I want to talk about is something we call in-place memoization. So because we want to memoize the result of the lazy evaluation, we can actually do so using the allocation of the lazy constructor itself. So you can see here that we have this sappend, which is the original lazy thunk, and we will return either an scons or an indirection node. And so if we look at this program down here, so let's say we have an sappend where we append the stream 1 to nil on top of S2. We want to be able to kind of use the memory of sappend itself to store the result of the lazy evaluation. So what we do to evaluate this is that when we first see the sappend, we of course match on S1, which is already evaluated. And so we see that we have to return an scons1, which we write directly into the memory of the sappend. And then we also have to, of course, allocate another sappend of the remainder of the stream and S2. And so if we continue doing this, so again, we can see that we enter up in the first branch. So we rewrite this sappend into another scons of 2. And we create a new sappend allocation, which in this case maps to null. And then finally, we are in the second branch of this definition, which means that we'll actually rewrite the sappend of null to an indirection node, and we'll keep evaluating S2. And so what we are doing in this example is we are always creating new allocation for the thunks, and then using that memory in place to store the evaluated results. And so I also want to contrast this a little bit to a different optimization that we call in-place reuse, which is actually quite different. because this in-place memoization happens even if there's more than one reference to the thunk, because it really implements this memoization behavior where all the references to the thunk should see the same memoized value in the end. But Coca actually has another optimization that we call in-place reuse, which also does an in-place mutation, but only if the reference count is 1. So if there's only one reference to the allocation. And so what happens then is that it can kind of generate this yellow block, so that's like some magic that the Coca compiler generates, where it can learn whether a cell is unique, and if so, it can take the memory cell of that cell and use it for another allocation. So here we will match on the stream S1, and we see if it's an S-cons. And so if it turns out that there's only one reference to it, we can use that space and use it later to allocate the S-append, the new S-append constructor in that place. Of course, if the reference count is higher, we have to do some extra work. We have to modify the reference counts a bit and allocate a new cell. So these are two very separate optimizations, but it actually turns out that you can use them together. So in this example, we can use in-place memoization to turn the S-append either to an indirection node or an S-cons. And we can use in-place reuse to dynamically see if the S-cons from the first stream, if it has a unique reference count, we can use that memory for the S-append cell. So if we look at this in this example, we have the S-append that we want to evaluate, and we'll rewrite it into an S-cons node. And if it turns out that the S-cons node from the first stream actually has a unique reference count, we will turn that one into the new S-append constructor. And then again, we apply in-place memoization to turn S-append into S-cons, and in-place reuse to turn S-cons into S-append. And finally, in-place memoization to turn S-append into an indirection node. And so the important thing about this optimization is that it means that if the first stream actually has fully unique reference counts, we can do a lazy append function with just one allocation, namely for the initial S-append lazy constructor, which ends up becoming an indirection node in the end. So we have benchmarked this, and we wanted to benchmark it in a setting where laziness provides no benefit. So we've looked at the heap and queues benchmarks or heap and queue example that Okazaki provides. And we made a benchmark where every thunk is evaluated, and in particular is not shared, which means that in this case, the laziness doesn't really benefit the program, but it allows us to kind of capture what the overhead of all of the allocations and so on that you need for laziness is. And so you have three systems. So this is only the first benchmark we have. So there's three systems. There's Coca, Ocaml, and Haskell. And the first bar on the left is the strict version, which we use as our baseline. And the bar on the right is a lazy version. And so we can see that laziness can have a pretty high overhead if it doesn't really benefit the program. So in Coca, the overhead in this case is even 5 times, because maybe Coca, laziness is not that well optimized. But even in a language like Ocaml or Haskell, you can have a pretty high overhead just from the allocations. But what we see here in red is that our version with lazy constructors can be much cheaper. And in particular, for the bankers queue, that one uses the streams with the append a lot, where we can save a lot of allocation and are a lot faster because of that reason. So to conclude my talk, the key ideas from this talk are that a lazy thunk can be defunctionalized into lazy constructors. The lazy constructors in particular are constructors which can be printed for debugging, for example, to inspect your program. They can also be memoized in place for better performance. And all of this is implemented in the Coca language, which you can try out. And if you want to see more examples of laziness, in particular of lazy constructors, please come to my talk in the Haskell workshop, where I'll also talk about lazy constructors a little bit. Thank you.
Hi. So it seems that all the benefits are operational, and there's like this closed world assumption about the whole thing.
Yep.
So why have the user write these? Like, why not do a whole program discovery and defunctionalization behind the scenes?
Yes, so you could also do this behind the scene. But in particular, I think it is nice to make the user write it because you can get good names for your lazy constructors, right? Like, I mean, so I mean, for example, you could do a whole program transformation that like just comes up with some name for each constructor, and then, for example, if you want to print it, just prints like a string that shows you the closure. But I think it can be a bit nicer if it's actually like a first order representation.
Yeah, but I mean, it's just a huge hassle because now it's very anti-modular. You have to put all your lazy function definitions in one place. They all have to be top level. So there's like a real cost to the human complexity of it.
That is true. You have to think about it a little bit more. Yes. So I mean, I've spent a lot of time looking at the data structures in Okazaki's book, and I think there it's actually very nice to use this interface. For several reasons. One is that there's not actually that many thunks. So in lots of Okazaki's data structures, there's like 2 or 3 different thunks types. And it's actually nice also when you're like thinking about your data type, not to think about, oh, this is like a tree which has like a weird closure in the middle, but to think of this actually like a constructor in your tree, so that like the constructor kind of preserves the tree shape. But yeah.
Okay, so hi, thanks for the very nice talk. I'm wondering how far you can go by just having maybe a simpler feature where you just allow constructors to have lazy fields, where you can say, oh, here's a constructor and one of its fields is lazy. Could you do a lot of what you're doing?
I'm not sure I understand how this would work.
Okay, well, the reason I'm asking is because this is probably the way I would do it in a language like Scala, where I believe you can already encode all of this in Scala, like most things. And so I wonder if you thought about this, about the object-oriented perspective on things, because this is getting quite close to the object-oriented perspective. In Scala, you can define enumerations, like algebraic data types with several cases, and they can have lazy fields. So these can represent the lazy constructors that you're presenting, and you could also similarly avoid allocations.
Okay. I'm not that familiar with the Scala approach to this, so we should maybe talk about this after.
Yes, let's talk about it more
break.
offline.
Thank you.
So I'm liking this result a lot. I'll be on the lookout for use cases for it.
Yes.
Something it seems to have a similarity to, though it's definitely very different, is codata. Because you have the idea of it's a constructor-like thing, but it's got some computation attached to it.
Yes.
Do you have any insights onto, are there actual connections, or is that just a surface level thing?
No, there's certainly a connection, and we also talk about this a little bit in the related work to our paper. I mean, I think in the end, the implementation is very different, right? In the sense that, for example, codata normally doesn't have memoization and stuff like this. But yes, there's certainly similarities.
Hi there, very good talk, really interesting stuff. It sounds to me like the definitions of lazy constructors that you've highlighted means that every lazy function you want to write, you have to sort of define upfront when you're defining the data type. Is that true? And if so, have you thought about ways that you might allow third party, as it were, lazy functions to be defined over existing types?
Yeah, so I think there's two ways to do this. So one is, so if you at the start create this sDelay constructor, then you can kind of, you can still add new lazy definitions to it later, but of course you don't get the benefits of other lazy constructors. I mean, there's some ideas like open data types, for example, that would get you maybe some of the performance benefits as well. Yeah.
Thank you.
Yeah.
So I have a question myself. So what I didn't get is what is the impact on the semantics of the data type? So if, like with regular laziness, you would have a sort of, you would allow just infinite structures with these constructors. So here you seem to allow infinite
Yep.
data types as long as they keep passing over a lazy constructor or something, or?
No, so we do allow lazy data. So we do allow infinite data types as well. And so we have
arbitrary infinite trees, right?
No, we actually allow arbitrary infinite trees. So you can, for example, create a new lazy constructor that like keeps adding like one element to the stream and then...
Yes, but I mean for one definition of a data type with lazy constructors, you don't get arbitrary infinite trees with the constructors, but your cycles are sort of restricted to follow what you define in your lazy constructors.
Yes. So I mean, if you fully evaluate the lazy constructors, you could get an infinite tree, but of course it's always suspended at some point using the computation that you've defined in the lazy constructors.
Yeah. So it seemed like an interesting sort of semantic result that you get, but I don't know if you've.
I'm not sure. I think all of this can also be modeled with regular laziness as well, but I'm happy to talk to you later.
Okay, maybe I should read the paper better.
Yes. Thank you.
Other questions? Maybe last question?
This is a very short question. Does the lazy constructor allows just the code to itself without any other extra structures? So like for example, in this case, sdelay app goes to sdelay app.
Yes.
If that kind of thing is allowed, then what happens if we match on that?
Yes, so you can define non-terminating computations in this case, and so Coca actually has an effect for divergence, and so we try to estimate whether we think your lazy computation will terminate or not, and if we think it doesn't terminate, then actually you'd get a divergence effect as well.
So it diverges when you pattern match on that?
Yes.
I see.
It can, yes.
Okay, so let's thank the speaker again.